Okay, so today we're going to talk about radian measure and a few related topics. So what is radian measure? Radian measure is just an alternative unit of measurement for angles. So just recall that we already have one unit of measurement for angles. That's degrees. That's how you've been measuring angles your entire life. And today we're just going to introduce a different unit of measurement, and that's radians. Now, before I sort of tell you what radians are, I just want to convince you of the following fact. To understand degrees, to understand the unit of degrees, what a degree means, what 90 degrees means, and so on, you really just have to understand one thing. So to understand degrees, you just need to understand that a full rotation, that's all the way around, a full rotation is 360 degrees. That's kind of all you need to know to understand what degrees mean. Once you know that a full rotation is 360, then you can say, well, what's a half rotation? Well, a half rotation would be half of 360, which is 180. What's a quarter rotation? A quarter rotation would just be a quarter of 360, which is 90. And you can see that sort of everything you need to know about degrees can be derived from the fact that 360 degrees gives you a full rotation. Okay? Now, the reason I mention this is that it's this kind of idea that I'll use to explain radians. To understand radians, this is the new unit of measurement. You just need to know that a full rotation is... Okay, so what is a full rotation in radians? How many radians does it take to give a full rotation? The answer is a little strange. It's 2 pi. That's definitely odd because 2 pi is an irrational number, and it's a bit strange to say that it requires an irrational number of radians to go full circle. But as we'll see, this is sort of all you need to know to understand radians. Okay? So we know that a full rotation all the way around is 2 pi radians. And from that, we can sort of work out everything else. So for example, what would be a half rotation in radians? Well, since a full rotation is 2 pi, a half rotation must be half of this, which would be 1 pi, or just pi. What would a quarter rotation be in radians? Well, since a full rotation is 2 pi, a quarter rotation must be a quarter of this. In other words, 2 pi over 4, which reduces to, you can reduce that fraction, and you get pi over 2. And every other angle that you can think of can be considered in this way. Okay, so now that we've sort of talked a little bit about radian measure, we now have 2 units of measurement between degrees and radians. And since we have 2 different units of measurement for angles, we should have a way of converting back and forth between these 2 units. So I'll tell you the formula, and then I'll prove to you that it's true. So let's talk about converting. So how do you convert between degrees and radians? Let's say you want to go from degrees to radians. All you do is you multiply by pi over 180. So for example, if you have 72 degrees, and you say to yourself, what is that in radians? All you have to do is take 72 and multiply that by pi over 180. Typically, you have to do some simplification to clean this up. 72 and 180 have a common factor of, well, at least 2 anyway. So 72 over 180, I can divide both of those by 2. I get 36. Here I get 90. So that would be 36 pi over 90. And yeah, I think that this can be reduced further, actually, right? I think these are both still divisible by 2 again, so I can divide by 2 again. That gives me 18 and 45, so that's 18 pi over 45. And then I guess these are both divisible by 3, so divide top and bottom by 3, I get 6 pi over over 15. Oh, geez, I'm really doing this inefficiently, aren't I? These are still divisible by 3, so top and bottom divide by 3. I get 2 pi over 5. That was a long process for reducing that fraction. So anyway, as you can see, all you need to do is multiply by pi over 180, but then you might have to reduce a fraction. Hopefully you reduce it more efficiently than I just did. Okay, now what about the other direction? Suppose you have something measured in radians and you want to convert it to degrees. How do you do that? Not surprisingly, you just multiply by not pi over 180, but actually 180 over pi. So for example, let's suppose that you have 3 pi over 2. That's an angle measured in radians, which is kind of obvious since it's got a pi in it. Radian angles tend to have a pi in them. So if you want to convert this to to degrees, you just take your angle and multiply by 180 over pi. And then simplify and reduce the fraction. You might notice the pi's cancel, and then we've got 3 halves times 180. This 2 goes into itself and 180 90 times. So all that's left is 3 times 90, which is 270 degrees. Okay? So that's conversion. Now, as far as why this works, I just want to convince you that this procedure actually makes sense. So basically, here's the following idea. I want a formula between the following two things. Theta sub d. Theta is the symbol that we use to represent angles typically. It's a Greek symbol. It's like an O with a little mark across it. Theta with a subscript d, I'm going to say this represents, so suppose I have an angle, okay, and theta sub d is going to represent the measure of that angle in degrees. So I have some angle, and theta d is the measure of that angle in degrees. And then I'm going to have theta r. That's the measure of the same angle, but in radians. And what I want is a relationship between these two quantities. So here's basically the idea. If I take theta d and I divide by 360, okay, think about what that's going to represent. Theta d over 360, that is the percentage or portion of a full rotation that your angle represents. Okay, if you take theta d, that's the measure of your angle in degrees, and divide by 360, then that's giving you the percentage or portion of a full rotation that your angle represents. For example, if this were 180, then you would have 180 over 360, which is 1/2, because 180 degrees is 1/2 of a full rotation. Over here, if I take my angle in radians and divide by 2 pi, this will also give me the percentage or portion of a full rotation that my angle represents, but in radians, because again, 2 pi is a full rotation in radians. So if you take your angle as measured in radians and divide by 2 pi, then you're looking at the proportion or percentage of the full rotation that your angle represents. The point is that these two quantities have to be equal. They represent the same thing, percentage of a full rotation that your angle represents. And because these two things are equal, I can actually solve for theta d or for theta r as needed. If I solve this for theta d by multiplying both sides by 360, for example, I obtain the following. And then you can see that this 2 cancels with part of the 360, leaving me with 180. And I find that theta d is equal to 180, and then I still have that pi in the denominator, so 180 over pi times theta r. So that's telling you that your angle as measured in degrees is equal to, well, your angle as measured in radians times 180 over pi, which is exactly what I told you the conversion formula was. So that's how you know these are true. And if you solve this thing for theta r, you'll see that the reverse formula that I gave you for converting in the other direction also works. Okay, so that's converting back and forth. Now, what I want to do now is talk about graphing or plotting angles. So in previous courses, you have obviously studied angles, but I would say that in all previous courses, whenever you studied angles, they were always in the context of a certain shape. Like whenever you looked at an angle, that angle was always sitting in the corner of a triangle or in the corner of a quadrilateral or some kind of shape. In this course, we want to be able to study angles outside of any kind of context. We want to be able to study an angle in and of itself, not embedded within a shape, but just the angle. So the question is, if you have some angle like 45 degrees or 60 degrees, how do you graph or plot or represent that angle if it's not embedded in the corner of some polygon? The answer is the following. Angles in standard position. So this is the way that we graph angles independently of any kind of shape that they might be embedded in. So here's the idea. Basically, I'll just draw a picture for you. So, of course, you know that an angle consists of two sides, right? So let's say that this is an angle, right? Maybe this is your angle theta. We like to say that the angle has an initial side. Initial just means beginning. And then a terminal side. That means ending. So, of course, an angle has two sides. Now, how do we graph an angle like this in standard position? What does that mean? Here's what it means. You make an xy axis. Okay, so this is x, this is y. What you do is you place the initial side of the angle along the positive x-axis. So no matter what your angle is, you always put that initial side pointing in the positive x direction. And then what you do is you just open your angle, you open the terminal side as needed, right, to create the desired angle. So the corner of your angle is at the origin, and you just, move the terminal side as needed to create your angle. So this angle here, put in standard position, looks like maybe it would be something like this. I do have one sort of comment to make, and that's the following. We will deal in this class with both positive and negative angles, and I have to explain what the difference is. If your angle theta is positive, then the convention is that your terminal side, this thing right here, opens in the counterclockwise direction. That's the direction opposite that a clock runs. So counterclockwise. On the other hand, if you have a negative angle and you want to graph it in standard position, again, you put the initial side along the positive x-axis. The only difference is that if your angle is negative, then instead of opening it in the counterclockwise direction, you actually open it in the clockwise direction. Okay, so that's the difference between positive and negative angles. Okay, so I think that might actually be, maybe just one example. So let's have a look. So I'll just do, one of these examples. So let's plot, say, pi over 2 in standard position. So one thing you'll notice is that this must be an angle measured in radians because it has a pi in it, right? You wouldn't write a pi in degrees. So this is radians, and we have to ask ourselves, what does this thing look like? Now, you could convert this to degrees, right? Using the formula, you'd convert it to degrees, and then you'd have a sense of how big this angle is. But I'm going to recommend that you try not to do this. You really need to come to grips with radian measure on its own terms. Converting to degrees is a little bit like, it's a method that you shouldn't use. You should have an intuitive sense for what radians mean. So what does pi over 2 look like? Without converting to degrees, can we figure out what it looks like? It all comes down to remembering that 2 pi is a full rotation all the way around. So what's the relationship between pi over 2 and 2 pi? We actually did this earlier, but if you think about it, pi over 2 is 1/4 of 2 pi. If you divide this thing by 4, then you get pi over 2, right? I mean, 2 pi is a full rotation. 1 pi is half a rotation. So 1 pi over 2 is 1/4 of a rotation. So this thing, pi over 2, is 1/4 rotation. It's positive, which means, so what do? I put my initial side of my angle here, and then I just open my terminal side until it reaches the desired angle. That's 1/4 of a rotation. Okay, so that's pi over 2. Okay, so that's what this thing looks like. And notice I'm drawing a little arrow to indicate the direction of motion. And maybe just one more of these. Let's try like negative pi over 4. Let's try and plot that in standard position. So what does that look like? One thing, as far as the size of this angle, how big is it? You might notice that pi over 4 is half of this. I mean, it's also negative, but in terms of its overall size, it is half of this thing. If you divide this by 2, you get pi over 4. So this thing must be like an eighth of a rotation, or half of this, but the thing is it's negative. And because it's negative, that means that the terminal side is actually going to open clockwise like this. So here is an eighth of a rotation like that. I guess that would be 45 degrees in degrees. Okay? All right, so I think that is, oh no, there is one more thing, and that's coterminal angles. So coterminal angles. So what are coterminal angles? Basically, coterminal angles are angles that have the same terminal side. Okay? What that basically means is, you know, I'll give you an example. Consider 180 degrees and also negative 180 degrees. Now, technically, these are two different angles, but if you plot them, they look exactly the same. So 180 degrees looks like what? It looks like, okay, that's like this, right? So there's 180 degrees. Now, negative 180 degrees would be the same thing, except, you know, you would open your terminal side counterclockwise, or excuse me, clockwise in the other direction. So here's the initial side, right? Negative 180, you would open the angle this way, and there's your terminal side. Now the thing that you see is that these two angles, their terminal sides overlap. They're in the same place. So these angles are called coterminal. Now there's lots of other examples that I can give you of these. Things like, for example, 60 degrees and negative 300 degrees. Those are coterminal. If you plot them, the terminal side lands in the same location. Now, I want to say, you know, can I give you a, hold on one second. I want to say, can I give you a sort of formulaic or more general way of talking about when two angles are coterminal? The basic idea is this. Angles are coterminal if they differ by a multiple of a full rotation. So here's what I mean by that. If you take an angle like 72 degrees and you add 360 degrees to that, in other words, you add a full rotation, that resulting angle, which is, I guess, 432. 432 and 72 are coterminal angles because they differ by a full rotation. Obviously, if you add a full rotation to an angle, you're going to land in the same place. You're just going around the circle a full time. I could add 360 again. Like I could take 72 and add 360 twice. That would be adding 2 full rotations, and that would give me some other angle. I guess that would be, let's say, 792, I think, if I add 360 again. So 72, 432, 792, those are all coterminal because, you know, they just differ by a full rotation. And you can also subtract full rotations. You can subtract 360, right? And you can add and subtract 360 as many times as you want. Now, if you're in radians, then you're going to add and subtract 2 pi, because in radians, a full rotation is 2 pi. So if you have like pi over 6, that's an angle in radians, and you want an angle which is coterminal with this, then you could just add 2 pi. And the resulting angle will be coterminal. It will be essentially the same because you've just added a full rotation. Now to simplify this, you actually need to treat that as a whole number and that as a fraction and combine them, which means you need common denominators. So you can think of this 2 pi as being 2 pi over 1, and then multiply top and bottom by 6 to obtain a common denominator. So that's 12 pi over 6. Now we can combine, we get 13 pi over 6. So pi over 6 and 13 pi over 6 are coterminal angles. And we could have subtracted 2 pi as well, and that would have given us others. So yeah, so every angle has an infinite number of coterminal angles associated with it, and they are all obtained by adding and subtracting as many full rotations as you like. Okay, so I think that's all I have to say for today.